In this circuit we have a load resistance supplied from a battery, and this resistance suddenly drops from infinitely large to 2 ohm resistance, which is exactly the same as internal resistance of the battery. And then at time of 1 microsecond this resistance rises back to infinity, and our task is to find capacitance of this decoupling capacitor such that the load voltage never drops before 0.8 E, 9.6 volt voltage, which means that at this instant of time this voltage may drop up to this voltage. Below we have calculations. The capacitance of this decoupling capacitor calculated is 196 microfarad. We may find this value by means of a piece-by simulation. At first, a non-schematic version, so we have to prepare a netlist. We have modeled our source by initial condition of a capacitor. So actually we are modeling this capacitor by initial condition, and obviously it's a value which is a variable. And here we have simulation. Well, we have to select performance analysis, then we have to add trace from goal functions. We have to select this goal function v sub 1 and 1 microsecond. Okay, the same, this is the result, and the same can be done by means of schematics version. So at first we have to prepare a circuit diagram using this library. We have to select C var in brackets as the value of this capacitance. Then we have to include this information in this box, which is here. And also it is quite important, as we have modeled this source by initial condition. So actually we are considering our circuit after changing position of the switch, and this value is minus 12. Why minus 12? Because we have to study the schematic netlist. Please observe that this voltage, I mean this is a plus, this is minus, so actually our voltage is voltage with arrowhead to this node, which is 0. Then our initial condition should be minus 12. This voltage is minus 12. Netlist has to be created and examined before simulation, as you can see, and we have corrected the initial condition. When the initial condition is corrected and analysis setup is completed, like here, we may, after saving this data, we may run simulation. We select all from possible values of capacitance. Then we have to select performance analysis here, because we don't want time on horizontal axis, we want value of capacitance on horizontal axis. So we have to select the performance analysis. Then from add traces we have to select the goal functions, these goal functions, from these goal functions, this one, which is y at x, our y voltage and capacitor voltage at x at 1 microsecond. And then OK, and this plot will appear now. Let me show you live how to operate. Obviously, having this curve, we may find a value of capacitance. Searching for the level of 9.6, we may find the value of this capacitance. Now, very briefly, the same but live version of presentation. Okay, circuit diagram already stored. So our capacitance, we have to double click here, yes, and we have to set its value is C, a variable, but initial condition is minus 12. Attributes are saved. also analysis setup, transient values. We've added a step ceiling this time, and sweep type decayed from 0.1 to 10 microseconds, well, 1000 points per decade. After saving, we may run a simulation. Yes, it takes, as you can see, few seconds, lots of calculations, even for this simple circuit. Then, okay, all values of capacitance, and we have a blank window. Now we have time. On horizontal axis, we have to press a performance analysis. Now we have our capacitance here, and trace, add trace, and the trace we are looking for is this. So this is capacitor voltage at time 1 microsecond. Okay, and having this, we have to search for the level 9.6. So here we have a capacitor voltage at 1 microsecond time, and searching for the proper level. .8 of supply voltage, which is 9.6. Okay, we find this value for 9.6 at 1 microsecond after changing position of the switch. For this capacitance, we reach this value. Okay, that way we have completed this problem. We have a completed simulation.